Hello everybody, welcome back to this series on trigonometry with college algebra. Today we will continue our review of the college algebra portion, specifically talking about functions and function notation. So let's get into it. Today we're going to start with the definition and how to recognize functions compared to relations. We'll talk about function evaluation and the difference quotient. I'll talk about piecewise functions and one-to-one functions. We'll start with relations. So a function is going to be a special type of relation, but a relation is a rule that assigns objects from one set called the domain. So sometimes we think about that as all of our input values, and it assigns them to another set called the range, which sometimes we call our output values. They're often represented by an ordered pair. So you can see in this example down here, we have a set of ordered pairs where the first component would be from our domain, those would be our inputs, and then the second component would be from the range, and those would be our outputs. We often consider the input values with this lowercase x, and we will use that a lot. So when we talk about the x value, even if there are maybe x's in the example, which might be confusing, when we talk about the x value, we're almost always talking about the input, and then sometimes we will call the output value y, or perhaps f of x if the function is called f, but we'll get into some of that as we go here. So we are looking at this example here. We've got this set of ordered pairs. We've got this one, 1, 2, 2, 4, 3, 6, 4, 8, and 5, 10. So again, all of the values from the domain are going to be from the first component of each of these ordered pairs. So if I would like to write my domain as a set, I could write that. So we use these squiggly brackets to denote that we are writing things in a set, and they often get sloppy for me, so I apologize in advance. But just listing them out here, we've got 1, 2, 3, 4, and 5 as the values from our domain. And from our range, that is going to be all of the second components here. So I'll point at those with a green arrow here. So the range is going to be 2, 4, 6, 8, and 10. And it is totally okay that some of those values are repeated in the domain and the range in the relation here. And we might even, try and see if there's some sort of relationship between the domain and the range here. And we might see that since these line up, that this is kind of like a doubling relationships where each of the outputs is just double the input. So we could write that in a more explicit way later on, maybe with some sort of equation or something. But right now, we can just kind of tell that all of the values in our domain are being doubled, and we're getting those values in our range. A function is a special type of relation. So I'm starting with relations, maybe just to go back, because, I remember always learning like how to tell what a function is, which of these, maybe we'll do some examples, which are functions, which aren't functions. And it's like, if it's not a function, what is it? Because clearly it exists. It's something that we're looking at. So more in general, we refer to relations, but functions are a special type of relation where there is some restrictions on the inputs and the outputs here. So a function is a special relation where each input value leads to exactly one output value. So that is no x value, no input value is repeated. If we have a function, we give it a name like f, or maybe g, or h, or k, or something. Most of the time we use f for function. And an input x we would call the output f of x, read f of x. So here we have some examples of some different, just very small domains, very small ranges. They're labeled here as inputs and outputs. So looking at the first example here, looking at A, we have a list of inputs, and we just want to decide if this is a function or not. So we need to see, does each input lead to exactly one output? So here we can see that P leads to M. That is going to exactly one output, so that's okay. Next, we've got Q, which is going to N. So that is also going to exactly one output. So we're okay there. And then we've got R here, also going to N. It is also just going to exactly one output. The fact that Q and R are going to the same output is totally fine. This is totally a function. Now later on in the lecture, we're going to talk about one-to-one functions, and then we might discover that that this is not a one-to-one function because several of the inputs are going to the same output. But that is totally okay for a function. There are examples of functions like quadratics and whatnot that are totally functions but are not one-to-one functions. So we'll talk more about one-to-one functions in just a little bit here. Looking at this next example, this one is even hopefully a little bit more straightforward in convincing you that this is a function. So P is being sent only to Q. We've got Q being sent only to Y. And we've got R being sent only to Z. So again, totally a function here. Every one of our inputs is being sent to exactly one output. So let's investigate example C here. Here we've got P being sent to X. But where we're going to run into some trouble here is that Q is being sent to both Y and Z. And here's where we have a non-example of a function. We have Q being sent to two different outputs. So this is not a function. So I haven't been keeping track here, but not a function. It is a relation. It is still a thing that exists and we can deal with. Relations are still important. We will see relations later on in this class that are still important in math. They're just not functions, which means that these inputs are being sent to multiple outputs, which has ramifications later. So just to maybe fill in the rest of the details here, this one is a function, check. This one is a function, check. This one, not a function. So going forward, we might see some other examples in the class where we need to figure out, well, what is a function and what is not a function. So again, just making sure that each input is going to exactly one output, even if that output is being hit by multiple inputs, like in the first example here. So evaluating functions, this is a very important thing here, and evaluating functions to me is a very straightforward process. That doesn't mean that it's always easy. For certain, we're going to see an example of a difficult function evaluation coming up in a future slide here. But this is essentially just substitution. So when given a function in formula form, so here we've got f of x written as a formula. It is saying take 5 and then subtract 3 times the square of x. And whatever we want x to be, we'll just substitute that in. We'll plug it in. We'll do a little arithmetic and we should be good to go. So when given a function in formula form, function evaluation works by substituting the given input in place of the independent variable. So here the independent variable is the x. That is what has independence. We can make it whatever we want. So what this is saying here in this first example is to just plug in 2. So what it's saying is just write down the formula that we have, and everywhere we see an x, we will just replace it with a 2. And I like to go over the top with my parentheses just to make sure that I'm getting exactly what I want. It's easy to make a mistake without putting in those parentheses, as we see maybe in this next example with the negative in it. But just to continue this here, I've got 5 minus 3. Now 2 squared is 4. So I've got 5 minus 3 times 4, which is 5 minus 12, which is negative 7. So the input for this function is 2, the output is 7. I could even maybe come back and write this as an ordered pair like we did early on. We don't have to, it depends on the context and what we're doing, but just to kind of come full circle with our original definition of a relation, I can write this as the ordered pair 2, negative 7, because my input from my domain is 2, my output from my range is negative 7. In this next example here, we've got f of negative 1. So again, we're just going to be using substitution. So what this is saying is, let me just rewrite the equation that I'm given, and everywhere I see an x, I'm just going to substitute in a negative 1. And then I can just compute my arithmetic here. So I've got 5 minus 3 times, now negative 1 squared is positive 1. So here we've got 5 minus 3, which, though maybe I'll even just write that out. 3 times 1 is just 3. So 5 minus 3 is 2. So here, if I wanted to write this as an ordered pair, the input value is negative 1. The output value is 2. Well, any of these here would be a correct answer in my book. This last example here, these always felt kind of weird to me when I was a student, because we're just going to be replacing an x with an a, which is just a different variable, and it was just kind of like, okay, who cares? Why couldn't we just started out with our independent variable being a instead of x? Well, there might be some reasons that we'll see going forward where we want a to not necessarily be our variable, but we do want it to be a placeholder for something else, maybe a constant value that we are leaving in general. So f of a, this one is maybe seems overly simple because we're just going to be replacing all of the x's with an a, so 5 minus 3a squared, and that's it. There's nothing left to do. So it sometimes feels a little unsatisfying to stop there because we haven't simplified and just gotten a single number or a single valued expression or something like that. But this is totally legit. We did exactly what we wanted, which was to substitute in an a everywhere that we see an x. So don't let that one weird you out. And as promised, we might see an example where plugging in some weirder values, h's and x plus h's, will feel a little weirder. So here we have the difference quotient, and it is just the name of this expression here. F of x plus h minus f of x all over h. What this does is it measures the average rate of change over this interval from x to x plus h, and it is super important once you get to calculus. You will use this as your definition for taking a derivative or finding a derivative. So it's a super important thing. It's often even presented in a slightly different way, but here we're using it in this form. And the idea here is we just want to use this function that we're given, and we're going to evaluate at f of x plus h. We're going to subtract off f of x. We're going to do a bunch of algebra and simplification, and what should happen is that h in the denominator here should cancel when we're done. If this h doesn't cancel, then I'm pretty confident that I must have done something wrong. So let's get into this, and we're just going to take this one step at a time. So trying to do this all in one step can be overwhelming. It's easy for even me to make a mistake as well. So what I'm going to do first is just look at evaluating f of x plus h. And again, I'm looking at my original function here, and this is a substitution thing. Anywhere I see an x in the given equation, I'm just going to substitute in x plus h. So I've got 2 times x plus h squared. So I'm just literally, for this x here, plugging in x plus h. I still need to square it when I'm done, and those parentheses are important, plus x plus h. So I'm putting those parentheses on again. Here they, are a little redundant because once we distribute kind of this addition here, nothing quite happens. But if that was a minus h in the a minus x in the original equation, then we would have to be a little bit more careful. So let me go ahead and just remind you that this x plus h squared is the same as x plus h times x plus h. Sometimes students get into trouble because they try and distribute that 2 exponent, but that would not be a property of exponents. If we had multiplication inside those parentheses, that would work. But here we just actually need to FOIL out x plus h times x plus h, and then we will add to that the other x plus h. You can probably see my dog just jumped on the bed behind me there. Hi, buddy. How you doing? He's a tired boy. He just got a bath. Okay, so continuing on here, I will FOIL out what we've got over here. So I'm going to keep this 2. It's just coming along for the ride. And as I FOIL out what we've got here, x times x is going to give me x squared. And then I've got x plus h and another x times h and another x times h, which is going to give me plus 2 xh's. And then finally I've got h times h, which is going to give me plus h squared. And then at the end here, we still have the plus x plus h. So now let me distribute the 2 inside here, and we've got 2 x squared plus 4 xh. Make that a little better. Xh plus 2 h squared plus x plus h. And now we can see if anything will combine here, and nothing really does. But now I've got what f of x plus h is. And as you can see, it's a little bit of a mess. So that's why I'm doing it kind of one piece at a time, and then we'll put it all back together once we're done here. So for the sake of my space management, let me just go get rid of the work that I did. If you need to reference this, just rewind the video. But I'm going to delete this for now, and I will move this guy over here. I'm going to get those equal signs to line up a little bit. There we go. So now what I want to do is write this together as a difference quotient, as a reminder, f of x is equal, or maybe I'll write it just again for space reasons. And maybe I'll color code as well, that f of x is 2x squared plus x. So now if I'm trying to write the difference quotient, what we've got here, so f of x plus h minus f of x all over h is going to be, so keeping with my yellow here, 2x squared plus 4xh plus 2h squared plus h plus x. And then from that, I want to subtract the f of x. So minus 2x squared plus x. And these parentheses are super important here because I'm subtracting off that entire function. So I need to put parentheses, that way I'm subtracting off the entire thing and not just the first term from that f of x. And this is all going to be over h once we are done. Sometimes I'll often just do this numerator by itself and then come back and put it all over h when I'm done, just to save myself a little bit of writing. But for completeness, I'll just put that here for now. In my next step, I'm going to distribute this here. So I'm going to have 2x squared plus 4xh plus 2h squared plus x. Let me make that x a little better. Plus x plus h minus 2x squared minus x. So again, distributing inside here. This is all going to be over h, and we should get some stuff to cancel in the numerator now. So if I'm looking, I've got a positive 2x squared here and a negative 2x squared there. They're undoing each other. Those sum to 0, so I can get rid of those. And I can see that I've got a positive x here and a negative x here. So I can cancel those out as well. So let me make a little bit of space here. Make a little bit of space. Can grab this, make it a little smaller. Then in my next step, come on, give me my colors. There we go. I'm just going to rewrite what is left here. So I've got 4xh plus 2h squared plus h. So 4xh, 2h squared, h. I think that's everything in the numerator. And this is all over h. Now, if you notice, there is at least an h term in everything in the numerator, which means I can factor an h out from every term in the numerator. So kind of coming up here, as promised, I will factor this h out, and what is left is 4x plus 2h plus 1 all over h. And like I had said earlier, if I've done this problem right, I know I can get the h in the denominator to cancel with an h in the numerator. Now that I've got it factored out, here's just that multiplicative 1. H over h is just 1. I don't need to write that. So, cancellation, as I've said in a previous video, is not something that's guaranteed. We have to find a reason to be able to cancel things. Here, finding that multiplicative 1 is the reason. And so our final answer will be, let's do it in blue, sure, 4x plus 2h plus 1. And you might be thinking, cool, like who cares? We got a new expression, like why is this important? But when you get to calculus, you will realize that this is insanely important, and you will be glad to have practiced this idea of evaluating a difference quotient, because from here you would end up taking a limit as h goes to 0. Don't worry about that too much right now. When you get to calculus, you will see a lot more of this. But for now, being able to practice simplifying this difference quotient will be a very important thing for us. All right, next on our list here is piecewise functions. So piecewise functions are defined by multiple subfunctions. So you can see I've got this function f of x, but depending on the interval of the domain, we assign a different subfunction. So I just kind of circled and underlined a bunch of stuff, but we can see if x is less than 0 in this example, so if I want to write that in interval notation, that's going to be from negative infinity up to 0, not including that endpoint there, means that we would substitute in to this subfunction here, negative x. And if we are looking at 0 to positive infinity, then we're going to use this subfunction over here. So hopefully to make that a little bit clearer with an example here. Let's see, that's not what I want. Here we've got f of negative 3. So depending on the portion of the domain, we need to figure out which subfunction to plug it into. F of negative 3, well, negative 3 belongs to this portion of the domain, which means we will use this subfunction. So what this is saying is f of negative 3, this is saying, okay, whatever the input is, just put another negative sign in front of it. So f of negative 3 would become negative 3 using the top subfunction there, which gives us positive 3. So our input, if I wanted to write this in that interval notation, or I'm sorry, in the coordinate kind of way here, we've got the input being negative 3 and the output being 3. So we're using the top subfunction there because negative 3 comes from that part of the domain. In the second example here, we're looking for f of 10. No, 10 comes from this part of the domain. It is bigger than 0. So this is saying for all the x's that are bigger than or equal to 0, where are we going to plug that in? We're going to plug it into this subfunction here, which says to square it. So what this is saying is f of 10 is 10 squared, which is 100. So if I wanted to write this kind of in this coordinate form, this would give us 10, 100. So input is 10, output is 100. For the first example here, the input is negative 3, the output is positive 3. So very different ways to address the inputs depending on what part of the domain that we're in here. And these happen in real life all the time because real life isn't as nice and neat as maybe some of these math examples lend to be. But piecewise functions, super important to know when, what part of the domain you're in and which subfunction to plug into here. So we're going to come back and graph a piecewise function, I think, in a little bit. But for now, we're going to talk about one-to-one functions. So a one-to-one function is a function, so it's already got to be a function. We talked about the difference between relations and functions. A one-to-one function is even a more special type of function where each output value corresponds to exactly one input value. So this is kind of saying the definition of a function in reverse. A function is making sure that every input just goes to exactly one output. Now we're saying make sure every output is coming from exactly one input. So maybe to go back to one of those first slides there, we said that a is a function, and I'll even give it a double check mark. But the fact that n is being hit by two inputs means that this is not a one-to-one function. So this one is not 1 to 1. Oops, 1 to 1. This next example B here, this is 1 to 1 because every output value is being hit by exactly one input value. So this one is, yes, 1 to 1. This one is not. And then we can't talk about C being a one-to-one function because it's not even a function. So it would make sense to consider its one-to-oneness, if I can say it like that, because it's not a function to start with. So that's the very kind of mathy definition there. Looking at some of these examples that we have something called the horizontal line test that can tell us which one of these are one-to-one functions. Well, we also have the vertical line test, which will tell us if they're even functions to start with. So looking at this first example here, first we can decide, yes, this is a function. Every input is being sent to exactly one output, and we can tell that because if I take these vertical lines, there's no portion of this graph that hits one of these vertical lines in more than one spot. So that's kind of a quick way to tell if the graph of a function if the graph of a relation is a function or not. And then we can tell if it's a one-to-one function by doing the same thing with horizontal lines. And here we can see that, for a lot of these horizontal lines, they're hitting the graph in multiple spots. So this would not be a one-to-one function. Let me go get rid of all that messiness there. But this would not be a one-to-one function. So this is not one 2, 1. And I could say because f of 2 is equal to f of negative 2 is equal to f of 0, which is equal to f of 2, which all have the same output of 0. So here there are lots of inputs that are all being sent to 0. There's 3 of them, which means that this is a function, but it's not a one-to-one function. In this next example here, if I take a look at some different horizontal lines, I can see that, yeah, it doesn't look like this graph hits any horizontal line in more than one spot. Maybe I should started with the vertical line test. I'll just tell you that, yes, this is a function. So after we discover that it is a function, is it one-to-one? Yeah, this is a one-to-one function because every output value is only being hit by one input value. So this one, yes, 1, 2, 1. And we can see that quickly using the horizontal line test. Horizontal. And then for this last example here, here we don't even need to consider the one-to-oneness, or if it is one-to-one. I don't know if that's an official term. I keep using it here though. Because just looking at the vertical line test, this would say, okay, not a function, because here I can see, well, let me maybe grab an actual value here. I just kind of did that randomly. If I look at negative 2 here, well, negative 2 is being sent to 0, and it's being sent to 1, 2, 3, 4. So not even a function in this case, because depending on, the input of negative 2 is technically being sent to two different output values. So here we don't even have a function. So not a function, not worth considering if it's one-to-one, because you have to at least be a function in order to be one-to-one. So we've got a list of just some basic functions here that are going to pop up over and over again. And it's nice to just kind of know the general properties of some of these functions and how to quickly graph a lot of these functions. It will be helpful to us moving forward. So the first one here is the constant function, which just says no matter what the input value is, the output is just some constant value c, where c is the constant. So in this example here, this one actually looks like it's f of x equals 2. If I go 1, 2, no matter what the input is, the output is always 2. So we can see, from this table here that negative 2 is being sent to 2, positive 2 is being sent to 2, 0 is being sent to 2. Everything on this line in the domain is being sent to 2. So we have this constant function, and c can be whatever. In this example, it's 2, but it could be 10, it could be negative 100, it could be pi, it could be any just value, any constant number that we want. The next example here is the identity function, which is f of x equals x, which means that whatever the input is, the output is exactly the same. So it's saying whatever the input is, the output is exactly the same. And we can see over here in our example, if we look at negative 2, well, that's being sent to negative 2. 0 is being sent to 0. 2 is being sent, positive 2 is being sent to positive 2. So again, we can see in the table over here that the outputs are exactly the same as the inputs, and that's why it's called the identity function. It is just the identity. Every input goes to itself as the output. And this is something that pops up a lot. It also just creates this very basic line shape, kind of the most basic line that you can think of, with a slope of 1, with the intercept going through y equals 0. We've got the absolute value function here, which is very similar to the identity function that we just looked at, but this makes sure that all of the outputs are positive. So, we can see here for 2 that it is being sent to positive 2, but negative 2, instead of being sent to negative 2, it's being sent also to positive 2. So what we had seen before is that this was continuing down that way, but now it's being reflected up so that all of these output values are now positive. So absolute value there. It does have this kind of point that comes down. It bounces, it hits 0 and bounces sharply back up the other way. We've got quadratics. Those are in the form f of x equals x squared, and we might do some different things to shift those around that we'll see maybe in a future lecture here. But this is saying whatever the input value is, square the output. So the square of -2 is +4. So we can see again that all of these negative values are being sent to positive values, and we're just going to square them to get there. Next, we've got cubic functions, which are very similar looking to the quadratics that we looked at before. So instead of coming up like this, so when we're squaring a number, if it's negative, it becomes positive. If we're taking a negative number and raising it to a third power, well, that will stay negative. So it doesn't actually do that. So this is why I'm saying they kind of look the same, but kind of like that absolute value, it's bouncing, reflecting rather over the x-axis. So this one is allowed to have the negative values depending on if the input starts as negative or positive. Next, we've got the reciprocal basic function here, which says whatever your input is, just do 1 divided by that input. Now, what we don't have here is 0 as an input. And in the next lecture here, we're going to talk about domains and ranges and restrictions that we can have on those. So here we would say that 0 is not part of our domain, because if we tried to plug in 0, if I tried to do f of 0, we would get an undefined value. So you can see that there is this asymptotic behavior at 0 where things are kind of zooming up and zooming down. And if you think about plugging in values closer to 0, you'll see that they'll either go towards infinity or towards negative infinity. We've got the reciprocal squared, which is very similar to the reciprocal, but we can see that everything is living in the positive world now. So we're allowed negative values, but once we square any negative value, it becomes positive. So now everything lives in the output value, the range where all of the range is positive. Next, we've got the square root, which has this shape here. And you can see that there are no negative values as part of our domain. We're thinking about real values here. I know we've talked about complex numbers, and those are totally legit, but we're thinking about having real valued domains here. And if we try to take the square root of -4 or something like that, so f of -4, we'd end up getting a complex number, and we can't graph that on this plane here. So while there, we can technically take the square root of a negative, there's no place on our graph, at least not the way that we have it here. So we are restricting our domain to only be non-negative numbers here, and we'll talk a little bit more about domains, like I said, in the next video. All right, well, it looks like it is time to practice. So with that, we will leave it here. In the next video, we will do a little bit more work talking about domains and ranges and how we find those domains and ranges, and we'll do some graphing of the piecewise functions as well. So I hope you have fun practicing, and I will see you in the next video.